Hello everyone, welcome back to my YouTube channel. In this week video, I'm going to explain to you how you should answer test 2 questions. Altogether, we have 4 different questions and let's start with the first one. Question number 1. In a chromatographic analysis of low molecular weight acid, solute A elutes at retention time of 8.63 minutes. Column void time is 0.25 minutes. And the retention time for solute B, on the other hand, is 6.98 minutes. Estimate the separation factor for solute A and solute B. Alright, so this is how you're going to answer this question. In this question, you were asked to estimate the separation factor. So in order for you to calculate the separation factor, first you need to calculate the retention factor. Alright, so looking at the formula here, for retention factor, we need to have retention time and the void time. So retention factor need to be calculated for solute A and also solute B. So what I'm going to calculate now is the retention factor for solute A. So the retention time for solute A is 8.63 minutes, and then the void time is 0.25 minutes, so divided by the void time as well. Therefore, the retention factor for solution A or solute A is equivalent to 33.52. Right, there's no unit for this. So I'm going to do the same for solute B. So the retention time is 6.98 minutes. And the void time is the same, 0.25 minutes divided by 0.25. Therefore, you will get the retention factor for solute B is equivalent to 26.92. So this is the retention factor, but you were asked to calculate the separation factor. Alright, so we have already calculated the retention factor, but you were asked to calculate the separation factor. So for the separation factor, the formula is alpha, which is the separation factor, equivalent to retention factor of solute A minus the void time divided by the retention factor of solute B minus the void time. So in the question, the void time is 0.25, so the rest is just the value that we have here. So 33.52 minus 0.25 divided by 26.92 minus 0.25, so you should get 33.27 divided by 26.67. Therefore, you will get your separation factor equivalent to 1.2475. Right? So this is the final answer. Let's move on to question number 2. Indicate how chromatographic resolution and retention factor differ from each other in the context of chromatography. Alright, so we will start with chromatographic resolution. So in resolution, we are going to assess the separation efficiency. Alright, so it means that this is the separation efficiency of the chromatographic method. Okay, and then it means that in order for us to look at the separation efficiency, it means that we are focusing on how well it separates adjacent peak. Alright, so the unit for chromatographic resolution is expressed in the unit of time, which is mostly in second. So this is the chromatographic resolution. Alright, so next we are going to look upon the retention factor. So in retention factor, we describe the specific compound interacts with the stationary phase and how it's retained in the column. So for example, if you have a column, like column chromatography, right? So you will have the stationary phase and also the mobile phase. So you have a stationary phase around here, and then you are going to pour in your mobile phase, and then we are going to put your sample. So in retention factor, we are going to look upon the compound interact with the stationary phase. So your sample, how your sample interacts with the stationary phase. Alright, so it means that how well it retained in the column. So basically, the unit for retention factor is dimensionless because it is the ratio of time. So in other words, we can say that when you calculate the retention factor, there will be no unit. So that is the differences between the chromatographic resolution and the retention factor. Next is question number 3. Calculate the wavelength in nanometer of X-ray for an unknown salt on a plane of 111 corresponding to the second order diffraction at 15 degree with a cubic lattice constant of 2.8345 angstrom. Alright, so in this question you were given the plane of the crystal. So when you were given the plane, definitely you need to calculate the d-spacing. So the d-spacing is equivalent to the cubic lattice constant, which is A, divided by the square root of h square plus k square plus l square. Right, so the value of A around here is actually the cubic lattice constant. So this cubic lattice constant given to you in the question is 2.8345 angstrom. Therefore, this unit should be converted to meter. Therefore, it is equivalent to 2.8345 times 10 to the power of negative 10. So we are going to transfer that value here. 2.8345 times 10 to the power of negative 10 divided by the HKL. So what is the HKL? Is this one. So 1 square plus 1 square plus 1 square. So it's equivalent to 2.8345 times 10 to the power of negative 10 divided by the square root of 3. So you should get your d-spacing equivalent to 1.6365 times 10 to the power of negative 10 meter. So this is just the d-spacing. Alright, so if we look closely to the question, you were asked to calculate the wavelength. So the wavelength, the formula that we can use is n times the wavelength is equivalent to 2d sine theta. Alright, so sine theta, so what is the angle? So the angle here is given to you in the question, which is 15 degree, and then you were given the information whereby it follows the second order diffraction. So your n should be equivalent to 2, and the lambda is what you are going to calculate, 2 times d. So the d is the one that you have calculated just now, which is the d-spacing, 1.6365 times 10 to the power of negative 10 meter sine theta. So your theta is 15 degree. Alright, so from here we can calculate the lambda, which is the wavelength, is equivalent to 3.2730 times 10 to the power of negative 10 meter. So this corresponds to this. And then your sine 15 is equivalent to 0.2588. Then this value you need to divide by 2. Therefore, you will get your lambda should be equivalent to 4.2353 times 10 to the power of negative 11 meter. Right. So, but be careful. If you look at the question, it states here that they want the wavelength to be in nanometer. Therefore, your lambda is equivalent to 4.2353 times 10 to the power of negative 11 meter. So from meter, you want to convert to nanometer, you need to times 1 times 10 to the power of 9. So you will get 0.0424 nanometer. So this is the final answer for the third question. Right, so we are now at the final question for this week's video. The differential scanning calorimetry (DSC) and the differential thermal analysis (DTA) are two distinct thermal analysis techniques used to study the thermal properties of material. They share some similarities but also have notable differences. Determine the two major differences between these analytical techniques. Alright, so I'm going to go briefly on how you should answer this kind of question. So we're going to start with DSC. So in DSC, the first information that you need to know that for DSC, it measures the heat change. So you need to write it measures the heat change. So, in terms of what? So, in terms of endothermic or exothermic. Okay, what else? So, this endothermic and exothermic is actually associated with the phase transition. Right. Apart from that, the DSC will measure the heat flow. So it measures the heat flow and it will quantify the enthalpy change. So associated with what? So it's this enthalpy change is actually associated with thermal events. So these are the information that you need to provide for the DSC. Okay, now we are going to move on to the DTA. So in DTA, basically the information that you need to provide is it measures the temperature. Measures the temperature of which the thermal event occurs. Alright, so what is the type of the thermal events? For example, it is the phase transition or chemical reaction So these are among the thermal events that can be measured by DTA. And then in DTA, specifically, it will measure the temperature difference So it measures the differences in temperature, temperature of what? So the difference in temperature between the sample and the reference material, right? So, but when it measures the temperature difference between the sample and the reference material, it needs to do that at the same heating and cooling process. Right. So these are the information that you need to provide in explaining the DTA. Alright everyone, this is the end of this week's video and the last video for this semester. So I wish you all the best for your upcoming final examination. So take care and be good. Goodbye.